It's a great pleasure to introduce Alberto Abbondandolo from Bochum. And Alberto will talk about middle-dimensional squeezing and no squeezing.
Thank you very much. Thank you very much for your nice invitation. It's really nice to be here. So the starting point of this talk is Gromov's non-squeezing theorem. I'm sure you all know it. It says that if you have a ball of radius r in R2n cannot be mapped by a symplectic diffeomorphism into a cylinder based on a circle of smaller radius, on a two-dimensional circle of smaller radius. And everything I'm saying today is joint work with Slava Matveyev. From Leipzig. But in order to start, I would like to restate Gromov's theorem in an equivalent but slightly different way as an inequality. So we have, let's consider a projector on R2n. So R2n is a projector, orthogonal projector onto a complex line, V. So R2n here is endowed with its standard symplectic structure, dp, dq, and its standard complex form. So this is a real two-dimensional plane, which is invariant with respect to multiplication by I, for instance, the plane P1, Q1. And then you can restate Gromov's non-squeezing theorem as an inequality. So phi, if phi is a symplectic diffeomorphism of R2n, I'll write it diff omega R2n, this is this symplectic form, then if I consider the ball of radius r, I transform it using phi, and then I project everything onto this two-dimensional plane, and I compute the area of this projection. This area is greater or equal than pi r squared. Okay, so this is Gromov's non-squeezing. Okay. It's apparently stronger than the usual statement, but it's actually equivalent just because area is the only invariant of area-preserving maps. So you have to use Moser theorem to show that it's equivalent. Okay. So this is Gromov's non-squeezing theorem stated as an inequality, and if you have this statement, there's an obvious generalization you can think of, which is instead of projecting onto a complex line, you project onto a space of higher dimension. So we have P. P now is a projector, orthogonal projector onto V, which is now a complex subspace of real dimension 2K. Okay? And you ask whether, well, you do the same, image of the ball, projection, and this time you compute the 2K dimensional volume of what you get, and you ask whether this is bigger than the volume of the ball of radius r in dimension 2k, which is pi to the k over k factorial r to the 2k. Okay? The volume of even dimensional balls is easy to remember. It's pi to the k over k factorial. So this is the question. This is the question I would like to address. And so this is a question on which I've thought a bit discontinuously, but for a long time. And yeah, and today I would like to tell you the state of the art about this question. So, so this can be considered as a sort of middle dimensional squeezing. So this is true for k equal 1, Gromov's theorem. It's true, obviously, for k equal n because, well, because in this case, this is the identity and symplectic diffeos are volume preserving. And the question, so in this case, there would be an equality. And the question is whether it's true for k strictly between 1 and n. Okay, and the first thing which we proved, let's say theorem 1, is that the answer is yes if phi is linear. Okay, in the linear, if phi is linear and symplectic, in the linear category this is true, and one can be a bit more precisely. In this case, the equality holds if and only if the image of V by the transpose of this linear map phi is also a complex subspace. Okay, phi is just symplectic. It's not a complex map. But if the image of V by the transpose of phi happens to be a complex subspace, then you have the equality. Okay, and theorem 2 is that instead the answer is no in general. And more precisely, so if k is strictly between 1 and n, then for every positive epsilon, there exists a symplectomorphism phi, diff omega R2n, which maps, say, so that the 2k dimensional volume of the projection of phi of the ball, say, of radius 1, is smaller than epsilon. In other words, you can make these 2k dimensional shadows of symplectic balls as small as you wish in volume. Okay? And the proof of this theorem 2 is, of course, is the construction of this phi, so it's an example. And this construction uses, so the proof uses constructions of Larry Guth. So Guth studied a different question. He studied the question of symplectically embedding one polydisk into another. And while doing that, he defined some very nice symplectic maps with very nice properties. And by combining his construction, adding little bit more, one can build these examples. Okay. Once you have a phenomenon which is true in the linear category and not true in general, the natural question is where is the border of validity of this statement? So, in particular, what can we say about, for instance, maps which are close to linear? Or in other words, say that we start with the ball. If we deform it by using a path of symplectic diffeomorphism, is it true that the volume of this projection can immediately decrease, or does it have to stay and maybe even increase and then only later on decrease? Yeah?
Just to make sure, V does not depend on x.
V does not depend, V is fixed. Yeah, V is fixed once for all. Okay, so we have fixed the projector and we built, now of course it wouldn't be true. Well, no, this I don't know. I don't know if it's possible to make it in such a way that the projection on all complex subspaces is small simultaneously. That's probably much harder.
Probably not by integral geometry.
But if it's not convex, it's a bit difficult. I mean, if it's convex, of course not. But if it's very strange, it's yeah. Okay. No, we're fixing the projector, and you can always think that this is always the projection to P1, PK, Q1, QK. Okay. And so yeah, I was saying, yeah. So the question is it true, I start with a ball, I deform it symplectically. Is it true that the volume of the shadow, of this 2K dimensional shadow, at the beginning has to grow and then maybe it can become small, or can it decrease immediately? This is the question. And and what I'm convinced now is that, so the first fact is true. So at the beginning, when you are in the local category, there is non-squeezing. So this volume of the ball at the beginning will actually increase, or say not decrease. So in some sense, in the local world, there are more symplectic invariants, which somehow, when you go far from the identity, they somehow disappear in some unclear way. So in some sense, this counterexample cannot be done in an infinitesimal level. It really uses the fact that the image of this ball will be strongly non-convex and there will be a folding, something like that. Okay, and in order to make this is only, of course, this opinion a bit more clear, let me state it in terms of a precise conjecture. So a precise conjecture is that if phi, so maybe let's write it. So if phi is C2 closed to linear, then this inequality, let's call it star is true. Okay, so for now, this is in this stated like this is still a conjecture. I don't have a full proof, but so the aim of this talk is to show. I would like to show you some pieces of evidence which should show that this conjecture is quite believable, that this is the situation. So, in order, the first piece of evidence is a computation, and in order to state this theorem, I need just to introduce some notation. So, let's consider if I have a loop, say of period 2 pi with values in R2n, I can associate two quantities to this loop. One is its Dirichlet energy. Energy of Z is 1/2 integral 0 to pi norm of Z dot square. And the other quantity is its symplectic action. Action of Z is the integral of the pullback by Z of a primitive. Lambda here is a primitive of the symplectic form. Okay, so energy and symplectic action. And there is an inequality between these two quantities. It's always true that the symplectic action is less or equal than the energy. I could actually here put also the absolute value, but let me write it like this. This is basically, a version of two-dimensional isoperimetric inequality. Or you can, if you express everything in Fourier series, you compare the two expressions. You prove that directly. And the equality holds if and only if Z, the loop Z, is actually a circle in a complex line parameterized with uniform speed. With uniform speed. Okay. This you can check easily by writing in Fourier series. So this is the first thing I need. The second object I need is the Grassmannian of complex lines in V. V is, again, this is our complex subspace. So, in other words, this is a complex projective space, and so these are complex lines in V. And this Grassmannian comes with its standard, it has a standard volume form. Let's call it eta. Eta is its standard volume form. It's the volume form which corresponds to the standard metric, Fubini study metric on the projective space. Okay, the last thing I need is that when I have a path of diffeomorphisms, of symplectic diffeos of R2n, then they're always Hamiltonian, and I can I can generate this path by using time-dependent Hamiltonian. In other words, the derivative with respect to t of phi t is xht of phi t. So there exists a path of Hamiltonians, so functions from R to n to R, in such a way that this is the flow associated to this vector field, where this is the Hamiltonian vector field associated to H. So it's J gradient HT, where J is the complex structure R to n. Okay, now with this object we can state a theorem. It's theorem 3. So let's say that we have this path phi t generated by ht, and starting at the identity. Phi 0 is the identity. Then, so if I take the volume of the projection of phi t of the ball, say, of radius 1, so this theorem is a second-order expansion. What happens in t up to second order? Of course, order 0, we start with the volume of the k ball, so pi to the k divided by k factorial. Order 1, we have nothing. This is good news. Order 2, we have, so plus a constant c t squared, so plus big O of t cubed, where this constant has an explicit expression. So this constant is an integral on the Grassmannian of complex lines in V. I will integrate with respect to the standard volume form on this Grassmannian. I denote L. L is the arbitrary complex line here in V. And here I write energy of ZL minus action of ZL, where ZL of T, this is a path. It's a path actually in V orthogonal, and it's, I take the Hamiltonian vector field induced by the Hamiltonian H0. I compute it along a great circle, e to the I t ZL, where ZL is an element of L, of this line L, intersected of norm 1, so boundary of the ball of radius 1. And then I take the projection 1 identity minus P. Okay, so maybe I'll make a picture. So this is my ball in R2n. This is R2k. Here I write a complex line because of lack of dimension. I write it as one line, and then on this great circle, so this is a complex line, so it has dimension 2. It intersects this ball on a circle, and on this circle I compute the Hamiltonian vector field, and then I take the vertical part, not the part on V, the part on V orthogonal. Okay, and this is what you find. So here the proof is it's a very long computation. It took us maybe 6 months to come up with this. And it's one of these accordion computation. If you want to compute the volume of the projection of the image of a ball by an arbitrary path of diffeos, you find very ugly formulas which tell you nothing. In the symplectic, if this is symplectic, there are a lot of miraculous cancellations, and eventually the formula is decent. And not only, but this constant is always greater or equal than 0. Because as I said, this energy is always bigger than this action. So, but of course, if you're generically, this will not be true, but if your Hamiltonian vector field is very special, it could happen that this path here is always a circle parameterized with a uniform speed in a complex line, and then these two things agree, and then everything vanishes. Okay? Yeah. That. Yes. Well, it comes out when you compute it and you write the formulas, but yes, again due to strict convexity of your ball. Yeah. No, this function is smooth. It's smooth for not only, it's a smooth function for T small. Okay. And okay, and another way of stating this this theorem is that if you consider on the group of diffeomorphism, the function which to a diffeomorphism associates the volume of this 2k dimensional shadow of the image of the ball, then this function has at the identity a second differential which is positive semi-definite. So a possible, a stronger conjecture of this could be that this function is actually convex in a neighborhood of the identity where on the where you put some linear structure, for instance, the linear structure induced by vector fields. This, of course, if it's convex, then of course this critical point would be a minimum, and this would imply this conjecture. And let me also write an addendum to this. But let me put it between parentheses. The addendum is that, so if I denote by, let me denote by f of t this function. The addendum is that either f has a strict minimum at t equals 0, or f of t vanishes up to every order at 0. It's small o of t to the m for every m in n. Okay? Yeah?
One that's not completely clear to me, even if you assume that C was always strictly positive, this statement here would be, it seems a little bit weaker.
It would be, it would be weaker, yes, because you don't.
In each direction.
Exactly, it's still weaker, yes. It's a directional version of this. So it would be weaker. Yes. Okay, I will say more on this addendum and why. Well, this is between parentheses because this is for now. It's nowhere written. Okay. So let me go on with piece of evidence 2. Erase everything. So piece of evidence 2 needs also a bit of preparation, and namely I have to introduce what is the Ekelenhofer capacity of a convex set. So, if I have a convex set in R2n, say smooth, open, convex, bounded set, then one can associate to it its Ekelenhofer capacity, which is the minimal action of a closed characteristic on the boundary of K, of C. So this is the minimum of the action, symplectic action of Z, where Z is a closed characteristic on boundary of C. In other words, it's a closed orbit of a Hamiltonian flow with the energy level boundary of C. Okay, and so this is the Ekelenhofer capacity, and there's a conjecture due to Viterbo, so conjecture of Viterbos, which says that this capacity should be bounded from above by the volume of the convex body. More precisely, this Ekelenhofer capacity of C, so it's controlled by the volume of C. Well, this is a 2n-dimensional invariant. This is an action, so this is a 2-dimensional invariant, so we need to take the exponent n to make them homogeneous. This is less or equal than this. And the constant here, the optimal constant, should be the constant that you achieve when you consider when C is the ball. When C is the ball, the constant you would find here is n factorial, because the capacity of the ball is pi. Here you have pi to the n, and the volume of the ball is pi to the n divided by n factorial. Okay, so this is our version of Viterbo's conjecture. Actually, in Claude's conjecture, he conjectures this for an arbitrary symplectic capacity, and also that the equality holds if and only if C is the image of a symplectic image of a ball. But this weaker version is enough for what we need now. And so something is known about this conjecture. Well, in the same paper, Viterbo showed that there is such an estimate, but with a constant n factorial, which is possibly worse than, with a constant which is worse than n factorial. So in Viterbo, so estimate with n factorial replaced by some constant Cn. Then Hartstein, Avidan, Vitaly Milman, and Yaron Ostrover showed that actually here the constant, so Cn, as Cn one can take a constant which does not depend on the dimension times n factorial. So in some sense, n factorial is asymptotically correct. But this constant for them is, yeah, it's bigger than 1. And then there is a recent result by Alvarez-Paiva and Balachev. I don't want to state the precise result. The result is that this sharp estimate, so with a equal 1, so it's the sharp estimate, but for a parametric version of this estimate. So this is still a work in progress. It's still not written. So yeah, I still don't know what will be the final statement that Alvarez-Paiva and Balachev will write in their final paper. Well, they have a one-parameter family. It's a bit like in this other statement. They have a one-parameter family of deformations, and they say that then they compute the ratio between this and the volume for this, and they say that either this function has a local maximum or it has to vanish up to every order. So starting from the ball. So it goes in the direction of proving that this is true for C close to the ball, but it's still far from actually saying that. But it goes in that direction. Okay. Okay, so this is Viterbo's conjecture. And an observation is that Viterbo's conjecture implies this conjecture on middle dimensional local non-squeezing. And let me explain you why. The key point is just that if I take a convex set C and I project it, by using this orthogonal projector onto a complex subspace, then its Ekeland-Hofer capacity increases in general. So the Ekeland-Hofer capacity of a projection is greater or equal than the Ekeland-Hofer capacity of C. This can be proved by using Clarke's duality. So of course, when you project, so this, in the definition you have this of Ekeland-Hofer capacity, you have this action of a minimal action of a closed characteristic. Of course, when you project a set, so closed characteristic will not be preserved, but since there is a variational principle behind, so this is actually also the minimum of a functional, and this functional behaves well with respect to these sort of projections. So this is true. And once you have this, you just start with the capacity of the ball, say to the n, which is pi. Let's take to the k. Capacity of the ball to the k, which is pi to the k. But this is also Ekeland-Hofer. This is also the Ekeland-Hofer capacity of phi of the ball, because of course, by definition, symplectic diffeomorphism preserve the Ekeland-Hofer capacity. And this is to the k, thanks. To the k. And this is less or equal than the Ekeland-Hofer capacity of P of phi to the ball, to the k. And now we apply the Viterbos. If Viterbos conjecture is true, we can go on. Here is Viterbo. And write k factorial times volume of P phi of B. Okay? So, and this is exactly, the volume is greater or equal, the volume of the shadow of the image of our ball is greater or equal than pi to the k over k factorial. Okay. Let me make a remark, so a small detour about this line. So notice that Viterbo conjecture is trivially true when k equals 1. So Viterbo conjecture is true for k equal 1, just because there is an equality here. This is capacity and the area in this case coincide. And so this means that this line actually gives you a proof of the classical non-squeezing theorem in Gromov situation when phi. Sorry, I forgot to say. Here the main point is that if phi is C2 close to the identity, then this is a convex set. Phi of B is a convex set, and also its projection is a convex set. Okay? So what I was saying is that this, so the above inequalities actually prove, this is not anymore a conjecture, prove Gromov's non-squeezing when phi is C2 closed to the identity or to a linear map. And what is interesting is actually that this proof doesn't use the local compactness of R2n, and so this proof remains true also for symplectic diffeomorphism of infinite dimensional Hilbert spaces. So it's so the Gromov non-squeezing theorem on infinite dimensional Hilbert spaces is still an open question whether it's true or not. In the 90s, Cookson showed that it's true when your symplectic diffeomorphism is a compact perturbation of the identity, basically because you can do a finite dimensional reduction. And this proof shows that it remains true also when your map is close to linear, which somehow makes sense. Okay. So this was piece of evidence 2. And let me conclude with piece of evidence 3. So of course, this is a strange piece of evidence, meaning saying that this conjecture is implied by another conjecture, but this other conjecture is 13 years old. It has resisted without no counterexample have been found, so at least it's. Well, in this case, everything would fall because since this is not convex, already this inequality is false. The fact that the echelon overcapacity increases under projection is a convex. It's a convex thing. It's a bit like the same why the echelon overcapacity is a capacity in the first place. It's sort of a similar. Okay. Yeah, so this C2 closeness is actually, it doesn't have to be too close. The only condition is that it's so close that the action, so close that the image of the ball is convex. Actually, not the image of the ball, because we need also convexity here. Yeah, this is what one needs. Okay. So piece of evidence 3 is instead, it's another theorem, not a conjecture anymore. And it says, so theorem 4 maybe. So now we change slightly point of view. We fix a symplectic diffeo. So instead of looking at a fixed ball and maps which are close to the identity or close to linear, we fix a symplectic diffeo, maybe very nonlinear, but we look at small balls. Using the fact that, of course, the behavior of a fixed nonlinear map on a small ball will be very close to its linearization. So in theorem, so let's now phi is a symplectic diffeo of R2n. Then there exists a subset of R2n which is open and dense. And there exists a function R naught on this subset A with positive values, such that for every point x in this set, the middle dimension no squeezing holds with respect to balls centered at x with radius smaller than R naught. In other words, the 2k dimensional volume of the projection of the ball of radius r center x is greater or equal than pi to the k over k factorial r to the 2k for every x, well, for every x in A is already there, for every r less or equal than R naught of x. So in other words, we can pick this, so this middle dimensional no squeezing holds for small balls where the centers are in an open and dense set. And of course, the conjecture, and this would be, so the first conjecture would imply that actually this set is the whole R2n. And again, an addendum. This is again an addendum which is again subordinated to these results of Alvarez-Paiva and Balachev, is that A is actually R2n when phi is an analytic. Okay, but this is still between parentheses. And let me just conclude just by saying just a couple of words about instead the proof of, well, not the addendum, the proof of this fact. So why do we have this middle dimensional squeezing for small balls here? So this is related to an integrability question, namely. So our data, the symplectic diffeo and our projector P, they induce what can be called a multivalued 2K dimensional. Sorry?
Is there a phi missing in your statement?
Ah, it could be, yes. Thanks. Yeah, it's again always the image of the ball of the, yeah. The other result is, yeah. A bit less into, okay. So now we have phi and P, and we can associate to this 2K dimensional, multivalued 2K dimensional distribution, namely to every, let's call it W. W of X is, this is the set of subspaces Y. So Y is in the real, this time in the real Grassmannian of dimension 2K in R2n. And these are the subspaces on which so if I look at the projection and then the differential of phi at X restricted to Y, this is now a map from a 2K dimensional space to a 2K dimensional space. I can compute its determinant. And this is greater or equal than 1. Okay, so I consider all those spaces on which the composition P phi is expanding 2K dimensional volumes. Since the linear statement is true, we know that this, for every X, this set of Y is non-empty. There is only at least one, sometimes even more. And what one can show is that if this multivalue distribution is integrable, where so let's say locally integrable, it's locally integrable, where locally integrable means that locally, if I fix a point, there is a neighborhood so that there is a foliation, a smooth foliation, which at every point is tangent to some of these elements, the natural definition. If this is locally integrable, then this inequality, again, star, 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 star holds for small r. And the reason is, well, technically it's complicated, but the idea is very simple. We have our point, this distribution is integrable, so we have leaves. These are 2K dimensional leaves. And then we have our map phi, and then we compose with our projection, and we go into our space V. And then the thing which is non-trivial to prove is that whenever, so if the ball is sufficiently small, this is a nice foliation by, say, by graphs, smooth graphs. And what can be proved is that in this case, if I have a 2K dimensional foliation of a ball, there is always one leaf which has at least the volume, the area of the ball in dimension 2k of the corresponding radius. There is a proof using minimal currents by Almgren, and there is a different proof using the Borsuk-Ulam theorem by Gromov. And if you use this fact, then you find a leaf which has big volume. So here there is one leaf. There exists a leaf L with 2k dimensional volume of L at least pi to the k over k factorial r to the 2k. But then now this composition is volume expanding, and then you're done. Okay? So this is one thing. And the second thing is that, so in general, if I have an arbitrary map, even an arbitrary map with the property that this composition has everywhere a big determinant, this distribution need not to be integrable. You can build easily, in the smooth category, you can build all sort of counterexamples. In the symplectic category, I don't know any counterexample of this integrability, and what we showed to prove this theorem for is that actually, so this distribution V is integrable on an open end-end set. And this uses the fact that the map is symplectic to get this integrability. Okay, I'll stop here. Thank you for your attention.